Welcome to the first lecture on generalized predictive control, index to minimize. We will review the minimum variance and generalized minimum variance control laws. We will point out the shortcomings of the minimization index. We will improve this index. Let's recall some of the noise models. Here is the Ormax model, Aremax model and Arix model. In all of these, a delay of k samples is present. Any change in u can affect y only after k samples, where u is the input and y is the output. There is a delay of k samples, and of course we have different noise models. Although there is a delay here, the noise starts affecting the process right away. It is just that it takes k units for us to find out. So we want to get the best estimate of the output so as to take corrective action starting now. The error term was split into past and future, and we also know that the best estimate of future noise is its mean. Let's also recall the prediction error model that we arrived at for the Ormax process. Here is the prediction y hat, and this is the Aremax model's prediction error model. Then finally we have Arix model. We will now take up the Arix model and recall the minimum variance control. Here is the prediction model for j, and then we will substitute j equals k and arrive at this prediction model at k, where k is the delay in the plant, and we let that equal to 0, solve this and get an expression for delta u. So here is delta u. This results in large control effort. Of course it is used only as a benchmark system. We came up with an approximate method GMVC by constraining u or delta u as the case may be. Recall that delta denotes difference, so delta u means the control moves or the difference between two successive control values. There are rigorous methods as well, because GMVC is approximate. The rigorous methods are GPC, Generalized Predictive Control, which we will introduce in this lecture, and LQG, Linear Quadratic Gaussian Controller. We will not discuss this in this course, but it is discussed in the book. Now let us take the generalized minimum variance control. We have seen this also. Let us summarize that. In the case of regulation problem of Arix noise model, we have to minimize expectation of this sum of squares. Here this script E denotes expectation. We minimize the variance of delta u also, unlike in minimum variance. In minimum variance we have only the first term, the second term got added in the case of GMVC. So we need to minimize this sum. By doing this, we keep delta u under check, and rho is a tuning parameter. In the case of servo problem, you minimize the difference between the reference signal and estimate of the plant output. We differentiate this expression with respect to delta u and equate to 0 to get control law. Once again, this is an approximate method. We pretend that we can differentiate through the expectation operator. Let's once again take the Arix model given here. We want y to follow r or the set point. Plant has a delay of k units as before, as indicated by z power minus k. So the earliest time when the current input un influences the output is n plus k. Thus we want the plant output to follow a reference trajectory n plus k onwards, that is not just at k but from k onwards. That is, we want to minimize the index of the following type: error at time instant k, error at time instant k plus 1, and so on and so forth. In GMVC we had only the first term. In GPC we add many more such terms. So here is the index that we want to minimize, but we also want to constrain U, that is the control effort, so as to avoid large control effort. Recall that we have delta in the RX model, so as a result the noise is present in the form of steps, integral of noise, so it becomes steps. It is not possible to constrain the value of U because noise occurs as step changes. We can only constrain changes in U. As a result, we add the following terms with rho greater than 0. In addition to this, we have terms of this type, where we want delta U n to be small, delta U n plus 1 to be equal to small, and so on. So delta U n will be U n minus U n minus 1. Recall the definition of delta, which is 1 minus Z inverse. This is what we had in the previous slide. We have expression for sum of squares of error and sum of squares of control moves. We want to minimize delta U terms up to n plus capital N, where capital N is some large number. Typically this capital N is a tuning parameter here. So rho is a tuning parameter, capital N is a tuning parameter. Because of control, if the control is good, y will be close to the set point at, say, soon after this n. U will become constant after n plus capital N. If the control system is well designed, U will become constant after this capital N moves, or delta U will become 0 after n plus capital N. So as a result, we need to write this up to n plus capital N only. Beyond that it will be 0. That is, U will become constant. But we monitor Y for a longer duration. That is, U is constant. As a result, Y keeps changing for some time depending on the dynamics of the system. After some time, Y will also become constant. So at which point you can stop adding terms. So typically you will have more terms here in the first two lines and lesser number of terms in the third line here. In any case, we need to add the delta U terms up to n plus capital N. So we will write that here, plus dot 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 here all the way up to n plus capital N. So how do we use this? We use the prediction model, determine y hat, substitute the prediction model here, and then solve for U and use that control law. This will be the approach that we would want to take in GPC. To conclude this lecture, minimum variance and GMVC minimize the prediction error at time instant k, which is the plant delay. This results in undesirable performance. This is improved in GPC by minimizing the prediction error over an interval. Minimization index includes delta U squared terms for RX and Aremax models. For Armax type models, it includes U squared terms. That is, U or delta U terms are also included over an interval. We will derive the GPC law in subsequent lectures. This brings us to the end of this presentation. Thanks for joining. Goodbye.